Okay, hi everyone, student. I want to continue our lesson. Our lesson is chapter 4. I don't know which class they already follow the chapter 4.1, but I still continue to teaching about starting with the chapter 4 lah. So hopefully you prepare the notes. There's a cathode-ray oscilloscope. Okay, let's see the notes. Okay, we start with the 4.1. The uses of the cathode-ray oscilloscope. Okay, so from here the oscilloscope, sometimes we using just a symbol or never symbol. I just see the short form C.R.O. Okay, CRO. So from here we need to learn about CRO. The first step, there's a thermionic emission. Thermionic emission is one of the process. Okay, let's see this one process, what they're talking about. Thermionic emission is emission of the electron. That means the electron, they will come out. Electron come out from where? From a surface of the heated metal. That means the metal, you need to heat it, or you go to heat method cathode. So we can say heated method. We also can say there's a heated method cathode. Okay, let's see the diagram here. Okay, this one is an example for thermionic emission. Okay, this one is a filament. Okay, the turning coil. This one is a filament. Okay, so from here, when I supply the battery, so I supply the battery means I hit the cathode. So after that, can you see the electron? They just happen, they just appear at the surface only. Surface. So that means the electron never move far away. They're just at the surface of the filament. So this one we call it as a process thermionic emission. Okay, the electrons still cannot go far away. They're just at the surface. Okay, why they can come in already heated. Okay, so this one we call thermionic emission. Okay, let's see one of the diagram about the thermionic emission. Okay, this one we call it thermionic emission. The hot filament, after that the electron, they just appear at the surface. Okay, then we go back to our lesson. Okay, now we continue with the following. Okay, now they need to explanation. Okay, explanation about the thermionic emission. A large number of the electron are moved inside the metal, but room temperature. Okay, inside, that means never surface, just inside the metal. That is happen in during the room temperature. The electron cannot escape at the surface because they are held back by the attractive forces of the atomic nucleus. That means they still got force to pull it to come back. They still cannot go outside. So this one is normal room temperature. Okay, let's see the B. When the metal is heated, some of the electrons have gained enough kinetic energy. So they gain the kinetic energy from where? From the thermal energy from heated. Then after that, they escape from the surface. So that means the conclusion is, if I never heat it, that's just at the room temperature. That means the electron cannot to come out from the metal. So if I heat it, then after the electron, they gain the kinetic energy, they will come out to the surface only, just surface. So this one process, we call it thermionic emission. Okay, now we're going to see some of the factor. Some of the factor to help the thermionic emission become better. So they make it become faster, thermionic emission. So we're going to see some factor here. We got 3 of the factor can be help the thermionic emission become better. Okay, let's see the first one, surface area. So that means when your surface area of the metal, okay, example, I'm using a filament, the surface is more. Surface more, the electron means more. Okay, electron more means when I just hit more electron, they will come out. So this one from here, they explain, as the surface area of the cathode increases, the rate of thermionic emission also increase. Okay, the second one should be the temperature. If I'm using the volt higher, so I find it the temperature to heat the metal should be better. So as the temperature of the cathode increases, the rate of the thermionic emission also increase. Okay, last one is a type of the metal. If I using the good conductor, means they're faster to heat up. So different type of the metal has a different rate of the thermionic emission. Good metal are tungsten, barium oxide, and also strontium oxide. So this one is an example how to increase the rate of the thermionic emission. Okay, now we're going to see the second part. Okay, second part we call it cathode ray. Okay, what means of cathode ray? Cathode ray is a narrow beam of a fast electron moving in the vacuum. Okay, cathode ray means the electron already escaped. That means they can move faster. So this one we call cathode ray. Okay, now you see the diagram. Okay, remember the first part. Now this one is the first part. This one is a thermionic emission. Okay, now the electron can go out already. So this one is the second part. We call it as a cathode ray. Okay, how to produce a cathode ray? Okay, let the electron can go through to the anode. This one is a cathode, is it? From the cathode, they can move to the anode. So can you see? This one got extra power supply that join with anode and also cathode. Before that, we just got filament supply only. Now they join another voltage between the cathode and anode. Means now your voltage increase. When your voltage increase means the temperature also increase. So that's why the electron now they gain more energy. So that's why they can move further. Okay, let's see the explanation. Okay, this one explanation they want to show about the characteristic of the cathode ray. Okay, cathode ray actually is what? Cathode ray actually is a narrow beam. They're formed by the electron to move. So we can call it electron, is it? So there's a negative charge particle. We also can call it there's an electron. Okay, now the electron, they move straight line. Okay, they move straight line. After that, they cast the sharp shadow. Okay, 3. They travel in very high speed and also have the kinetic energy. Okay, D, they can cause about the fluorescence. Fluorescence means the process where the kinetic energy of the electron, they convert to the light energy. Okay, last one, they can deflected by the electric and also magnetic field. So this one is all characteristic for the cathode ray. So later we need to prove, is it this all characteristic is correct or not? Okay, so we're starting to introduce first. Okay, let me see some of the diagram about the cathode ray. Okay, this one is a diagram to show the cathode ray. Can you see the extra to add 400 volt? This one we call it extra high tension. Okay, extra high tension. When I just join with the filament and also the anode. So you'll find it the electron now, they are accelerate, move faster in this area. Okay, so this one we call cathode ray produce. Okay, then we continue the lesson to prove one by one the characteristic. Okay, now we're going to see this one diagram. Okay, this one diagram they join together. From filament go to anode, then join with the Maltese cross. This one is called Maltese cross. They're just one of the cross they put at the center. Then this one we call fluorescent screen. So later the electron they will strike to this one screen. After that they produce a fluorescent color. Okay, so from here let's see how to function. Okay, the design of the cathode ray tube and also how it work. Okay, this one is an extra high tension. Okay, now we're going to see we're starting with the filament. Cathode ray tube consists vacuum tube. This one we call vacuum tube. Okay, vacuum. Then after that we got anode. Okay, where's the anode? Anode is here. Okay, this one we call anode. Okay, after that we got cathode. Cathode is a filament. Okay, after that and heating filament and also the screen. Screen actually is a filament, the fluorescent screen. Okay, now B. The vacuum tube is an vacuum glass tube. Okay, the vacuum tube means the whole tube here must be vacuum, don't have any A molecule. If got A molecule, they will affect the electron how to deflect it. So from here must be vacuum. Okay, C, anode. Okay, can you see the anode center? They got one of the small hole. Okay, they never block all. They just draw like this. This one, the small hole. Okay, this one hole for what? This one hole for the electron to move. So they want to focusing the electron go through straight line. So this one is a function for this hole. Okay, D, the cathode is heated by the tungsten filament. Okay, we're using the tungsten filament because tungsten filament is a good conductor and produce more in the electron. Okay, now we go to E. Okay, E is the heated cathode emit electron and also accelerate at high speed. Okay, accelerate at the high speed from where? From the anode and also cathode. Why they can accelerate? Because they produce high voltage. Okay, they supply by the high voltage from the extra high tension. So that's why you see the extra high tension, they join between cathode and also anode. So if the question asks from the cathode to anode, how the motion of the electron? So the motion of the electron here is a accelerate. Okay, acceleration, go faster. Okay, now we go to F. After the accelerate, okay, the fine beam electron means the cathode ray, they will strike to the fluorescent screen. Okay, after that they strike to the fluorescent screen, causes the green screen fluorescences with the green light. So that why they produce a fluorescence of the color, there's a green color. So we can say that one is a cathode ray produced. Okay, so we're going to see some of the diagram to show the cathode ray. Okay, so this one is a diagram. Okay, we're starting with the filament, cathode. After they go to the anode. Okay, after the anode, they go straight. After that, they hit to the fluorescent screen. After hit the fluorescent screen, they find it. They're just one of the bright spot. This one bright spot is a green color. Okay. Okay, then we continue with the investigation. So we need to investigate one by one. Is it the characteristic of the cathode ray is correct or not? Okay, now the first step, they want to investigate the properties. There's a Maltese cross tube. Okay, they put a Maltese cross tube at the center. Okay, later they want to see, is it the cathode ray go straight or not? Okay, now we're going to see the procedure. First one, 6 volt heated supply. So this one is a normal heat, normal voltage. Observation, a shadow of the cross is seen. Sure got shadow, is it? Because you put one of the shape of the Maltese, you cross at the middle. So when I just on the light, when I'm using 6 volt means I just on the light. When I just on the light, this one is thermionic emission, is it? The electron is never moved. So you find it, they will form of the shadow. Okay, one of the part they will blocking by this one Maltese. So the shadow of the Maltese cross they will produce. Okay, now we go to explanation. Why got shadow? Okay, the shadow is formed by the ray from the heated filament. Okay, if you don't have any light, you cannot see the shadow. So that's why when I just heat the filament, they produce a light, is it? So I can see the shadow at the screen. So conclusion, I can make it light ray travel straight line. Okay, if they never travel in a straight line, I cannot see the shadow exactly on the screen. Maybe they've deflected. So from here, I can prove now the light ray is travel in straight line when the thermionic emission. Okay, this one is an example. So cathode ray, when I just on, so you find it, the Maltese cross block at the center, then you can see the shadow. So this one, they prove the cathode ray is a go straight line. Okay, this one is a example. So when I just on, then you find it, this one is a Maltese cross at the center. So the light will pass through the Maltese cross, then they will block at the center. So I form a shadow. So you can see a shadow, big shadow on the screen. Okay, so we go to next one, the explanation for the second characteristic. Okay, student, then we continue with the page number 2. This one is want to test about the properties of the electromagnetic field. Okay, this one not electromagnetic field. They want to test about the cathode ray. Okay, when you see this one, the first one they're using the procedure. They start with using the 6 volt. Okay, using the 6 volt, there's a original. There's when starting they want to hit the filament. Okay, now can you see they add one more? There's a 3 kilovolt power supply. So this one we call EHT, extra high tension. They're connected between the cathode and also to the anode. Okay, when I just add this one means what? The voltage will be increases. Now observation, they see they got green shadow of the cross is seen same size at the same position as the shadow formed by the light. So that means just now you see the one of the Maltese cross. Okay, I draw the Maltese cross. Okay, this is a Maltese cross. Then surrounded, just now is a yellow color, is it? So from now, when I just on the EHT, so you find it now, they got 2 of the shadow. Okay, overlap each other. That means the shadow become darkened. Surrounded now become green color. Okay, just like the diagram they show. Okay. So from here, the shadow is formed by the cathode ray. Conclusion, what we can conclude, cathode ray, they carry from the kinetic energy. After that, they strike to the fluorescent screen. After that, they convert to the light energy. So from this one, we want to prove about the energy convert. From the kinetic, they straightforward convert to the light energy. Okay, so this one is one of the properties they want to prove. Okay, so from here I will show about the diagram about the cathode ray to produce. Okay, let's see here. So this one is a cathode ray. Okay, can you see the center is a multi-cross? So when I just on the light, that means the cathode ray they pass through, the whole tube they will produce a green color light. So this one green color light they represent by the cathode ray. Okay, this one also same. So can you see the shadow? Okay, actually here got double shadow. Okay, base is a yellow color, then at the top should be the green color. Okay, so this one is more clear, exactly in front of the vacuum tube. So you find it, this one center Maltese cross, this one shadow, then surrounded by the green light. Okay, so they put the screen, the fluorescent screen, then you can see the green light is more clear. Okay, so this one they just want to prove the kinetic energy convert to the light energy. So we go to see the following one. Okay, then we go through to see the following, what is the properties. Okay, next the properties is a magnetic field. So this one same like the just now diagram I show you. Okay, center is a shadow surrounded with the green color. Okay, now a bar of the magnet they brought closer to the cathode ray. Okay, 2 shadow now you can see by the screen. Okay, when you put the magnet bar closer with the cathode ray, you find it. One of the shadow they will move. That shadow move one sure is a cathode ray. The original one, that means the filament you go to hit thermionic emission one, that one is the original, that one static at the center. So now they say 2 shadows seen on the screen. Now the light shadow remain. Okay, at the center, the light shadow. Okay, the dark one they will start to shift. Okay, the catapult force is produced because of the cathode ray carry the charge. Okay, conclusion, cathode ray can be deflected by the magnetic field. Okay, this one how to deflect, we need to depends by using the Fleming left hand rule. So either the shadow move up or either the shadow move down. Okay, maybe your notes a little bit changes. Okay, you see my note first. This one is a north. This one is a south. So from here, we're going to need to point about the north and also the south. Okay, we're going to see first. Okay, so from here, you need to show about your left hand. Okay, north. So I take out my left hand. North. You need to point like this. Okay, north. Okay, north to south. Okay, now your second finger is represented by current, is it? Current actually far away from you. Agree or not? Because this one is one of the vacuum tube. Okay, vacuum tube inside is a electron. Electron now is come to your side. Electron come to your side. So that means should be electron come to you. The current is always opposite direction with the electron. So now the current is far away from you. So that means you need to point left to right. Okay, I don't know if you can see or not. Left to right. Okay, after that, second finger you take out. Point far away from you. Okay, point far away from you. Can you see my thumb? I'll show here. My thumb is point to up. My thumb point to the up. Means the shadow will shift to the upwards. Okay, shadow shift to the upwards means when you draw the magnetic field, bottom must be curved. Okay, bottom you need to draw curve. Okay, means bottom becomes strong. Then they push, the force go up. So you find the shadow is moved up. Okay, follow your notes. I find it the pole is different. They put the north pole as the left, south pole is the right, is it? Yeah, better you go to shift. Okay, I don't know correct or not. So I'm using the old one. So you refer the diagram I show you. This one should be correct. Okay, so from here I will show you some of the video, let you to see about the magnetic field effect to the cathode ray. Okay, let's see here. So you can repeat it to see it by pause lah. You pause and see the magnetic field, then you show your Fleming. After that you see correct or not the direction of the shadow. Okay, then we continue for the last one. The last one should be the deflected by the charge. Okay, can you see the inside the tube they got extra one of the plate? Okay, positive and negative plate. Okay, now they want to detect it. Is it the electron negative charge or not? So they want to test it. So first thing they're using connected deflecting cathode ray tube using the 6 volt. Okay, now AC power supply connected to anode to the EHT. Okay, must EHT, if not cathode ray cannot come out. Okay, observation. When starting, there's a no voltage. So they fired it, the ray just goes straight. Nothing happened. Okay, when the top they connected with the positive, down is a negative. So you find it the cathode ray, they're bending. They bend to the upwards. Okay, if I reverse again for the terminal, then you find it. Cathode ray also deflected, but deflected go to downwards. Means when the cathode ray, they keep want to find about the positive charge. Okay, so from here, this one is explanation. First one, no deflection. Another one go to upward. Another one go to downward. So the explanation here is electric field that between the two plates. Okay, conclusion, cathode ray is negative charge. So we can prove about the cathode ray, there's a negative charge. That means they keep want to find the positive charge. Okay, so this one is another properties. Okay, we need to show about the cathode ray. Okay, let's see the diagram. One of the diagram also show about this part. Okay, so cathode ray goes straight. Okay, when they put about the charge, down is a positive. Okay, then they will deflected, go to the downwards. Okay, so this one is a one of the demo. Okay, then the following should be the type of the motion. of the cathode ray and also the energy conversion of the electron. So that means you need to know about the motion and also the electric energy, how to convert. Okay, let's see the diagram here. Type of the motion. Okay, motion we just explain velocity and acceleration only. Okay, energy convert. So that means we need to learn two things. One is the motion and also how the energy convert. Okay, let's see the part that's separated by the PQR. Okay, PQ is a cathode to anode. Okay, how about the motion? Cathode to anode must be accelerated, is it? Because you join EHT. Okay, now here is a EHT. Okay, so that means electron here must be very fast. P to Q, they move in a fast. Okay, electron move very fast. So from here I can say there's a velocity increase, or you say uniform acceleration. Okay, now you see the QR. QR is no more, don't have any extra high tension. Okay, means the electron here, they will go straight to the screen, is it? So this one we just say uniform velocity. Okay, normal velocity. Okay, now we're going to see the energy convert. Okay, let's see the P. P is a cathode. Okay, when starting the cathode is what? Heating, is it? You heat, let the electron come out to the surface. So this one we call electrical potential energy. Okay, remember potential energy we learned before? We learned about gravitational potential. We get elastic potential. When you see the word potential, means they're ready. They get ready. Example, gravitational potential energy means they get ready to come down. Elastic potential energy means they get ready to compress, or they want to stretching some of the thing. Okay, now electrical potential energy means they're ready to let the electron to come out. So we call it electrical potential energy. Okay, now we're going to see the anode to the screen. Okay, anode to the screen, there's a QR. Anode go to the screen. So anode go to the screen is what energy that changes. There's a kinetic and also light energy. Okay, electron move fast, uniform velocity. Hit to the screen, they produce the light. So from here, kinetic energy convert to the light energy. Okay, then we're going to see to determine the velocity of electron. Okay, let's see here. The moving electron, we want to count about the velocity. We need to count is starting from the cathode to the anode. Means when they are accelerate. So we need to count. Okay, let's see the formula first. See the page number 3. Okay, we need to know is formula, is it? Okay, this one is a principal conservation of the energy. Remember this principle, what they're talking about. Okay, this one principle means before the process, your energy is how many? Must equal total energy after. So they just like the momentum conservation. So energy before must transfer to the total energy after. This one we call conservation of energy of the electron. So before is what? Before is a thermionic emission. So before we call it there's an electrical potential energy. Okay, after is what? After is a kinetic energy because the electrons start to move. So we can write the equation actually is a EV. EV is a potential energy of the electron equal half mv square. Okay, both V is a different. One is a capital, one is a smaller. So if the question they want to find the velocity, so V must be equal EV multiply with the 2 divide by the m, then you need to square root. So this one is a formula to find the velocity. Okay, let's try the example 1. Okay, potential difference between the anode and cathode of the electron gun is a 5 kilovolt. Calculate the kinetic energy of the electron. Okay, so from here we can write about the equation. EV equal half mv square. Okay, now the question they want to find kinetic energy, is it? You want to know kinetic energy, you must know the velocity. So from here we don't have. So if we don't have, it's straightforward to find the EV, that's all. Because the EV also same like the kinetic energy. So I just apply 1.6 times 10 power of negative 19. then multiply with the 5 kilovolt. Okay, so the final answer I get it is 8 times 10 power of negative 16. Remember, energy, that is joule. So this one answer for example 1. Okay, then we go example 2. In the vacuum tube of the TV receiver, a cathode ray is produced and accelerated through the potential difference 7 kilovolt. Determine the velocity of the cathode ray. So we still write the same equation. EV equal half mv squared. So now the question, they want to find velocity. So velocity equal 2 EV over m, then square root. Okay, or you must convert this one 7,000. So finally I get the answer from here after square root 4.99 times 10 power of 7 ms negative 1. Okay, so this one is a final answer for the velocity of the cathode ray. Okay, so I need to continue. Then we go to the main part lah. The main part is a cathode ray oscilloscope. Okay, cathode ray oscilloscope, that's separated by 3 parts. Okay, we label here already 1, 2, 3. Okay, let's see the first part. First part is a starting part. That means from the cathode to anode. This one we call starting part. Okay, second part we got deflection part. We got Y plate and also the X plate. Okay, third part is the vacuum part. That means when the electron beam they want to hit to the screen. So this one is the third part. So from here we're going to see one by one the structure. Okay, A. Okay, the first part we call it electron gun. Okay, they produce a narrow beam of the electron. Okay, now we're going to see first one sure is a filament. Filament, you heat the cathode at the high temperature. Okay, number 2 is a cathode. Cathode that emit the electron from its surface after heat up. Okay, after that we got control grid. Okay, control grid is control the number of the electron which reach to the anode. So this one is a filament. The electron will come out, is it? This one is your, this one is the anode. Okay, this one is the anode. So that means control grid, they can control the number of electrons that reach to the anode. That means conclusion, we can say they control the brightness lah. If more electron can go, that means more brighter. If the less the electron stop, that means your bright will be lost. That means they will show on the screen become dim. Okay, then we say focusing anode. Okay, remember focusing anode is come from the anode. Okay, remember I told you anode got one of the hole. This one hole they want to do as a focusing. Okay, focus all the electron to form a narrow beam at the screen. So that means if the hole becomes smaller, that means you find it the light, the cathode ray later they produce is more sharp. Okay, last one is the accelerating anode. Accelerating anode, the function is accelerate electron beam to the high velocity. Okay, so this all is a function for all the component in the electron gun. Okay, then we're going to see the second part. Second part is a deflection system. Okay, deflection system, we just got 2 plates only because they want to deflect the electron beam. Okay, Y plate. Y plate is to move the vertical beam. Okay, the Y plate just like up and down. Okay, up and down, that means later your electron just come, they want to deflect it up. So this one, we call it as a Y plate. That means they can produce the line should be vertical line. Okay, if X plate is how? X plate means left, right. So when the electron just come, they deflected either left, either to the right. So that means this one can produce the horizontal line. Okay, X plate to move the electron beam vertical. Y plate, X plate is to move the electron beam horizontally. Okay, last part is a fluorescent screen to show the display of the wave to produce. So inside the screen, they got graphite coating. They want to produce a light when the electron beam strike. Okay, so this one is a simple diagram of the CRO. Okay, I will show some of the diagram lah, for the CRO. Okay, this one is a diagram, exactly same as your notes. So we need to know every part lah. We got power switch, we got focus, X shift, Y shift, after that time base and Y gain. Okay, from here, which one should be the important? The important is a Y gain and also the time base, because later we need to do the calculation from these two information button. Okay, then we continue to see the next one. Okay, this one is a cathode ray oscilloscope, what they will show on the screen later. Okay, they're just like the one of the wave pattern. Okay, this one is what you need to know. This one is the actual one in the lab. Okay, this one is a screen. Okay, can you see the green color? The green color is a cathode ray. Okay, you can adjust the button here to make it become more sharp or more brighter. So this one is the function for the control grid and focusing. Okay, so this one is a diagram what I want to show you. Okay, then the next one I need to know is every structure. Just now I show you this one, is it? This one, 13. This one, all the part here we need to know function. Okay, I will show one by one. This one is in your notes. There's a page number 4. Okay, let me open the page number 4. Okay, so this one is a page number 4. Okay, we can go and see. Okay, go to see your page number 4. Okay, this one's page number 3. Then we go to page number 4. Okay, so from here we can see the first part, the switch on and off. This one is a normal switch. Should on the CRO or not. Okay, brightness. Okay, brightness. Okay, this one want to control the intensity of the bright spot. That means let your bright spot become more clear or not clear. Okay, you can say about the sharp or not sharp. Okay, after that we got X shift. Okay, X shift means they want to control the direction is moving horizontal. They call X shift. Okay, so I draw here. Okay, this one is X shift. Okay, when starting at the center, is it? Okay, this one is the center. Okay, maybe your graph like this. Your graph is too low already. So you adjust the X shift left or right. This one we call X shift. Left, right only. So Y shift means up, down. So if your wave is too low, you can adjust up or you can adjust down. Maybe your wave now go up already. This one we call Y shift. So you adjust the vertical position of the bright spot. Another one, X shift, that means you adjust horizontal. Okay, Y gain is what? Y gain is a voltage. Okay, one of the button to control the voltage. Okay, voltage. Spelling also wrong. Okay, voltage. Okay, voltage. Okay, voltage. So this one is control the voltage. They set the magnitude of the vertical shape of the spot on the screen. Okay, vertical. They just read vertical only. Okay, time-based control. Time-based control means that later you need to read about the period lah. Okay, the time. This one how to read? This one we read by the horizontal line. Okay, Y gain is a vertical line. That means Y-axis. This one is the X-axis. So from here they apply the changing the voltage on the X plate, which make the spot move horizontal line at a steady frequency. So later I show you how to count lah. Then we got X input to connect the source to the potential different X plate, and the Y input to the Y plate. Okay, last one is a AC or DC, selected according to the type of the input. So important is a Y gain and time base. So later we see how to find about this all thing. Okay, CRO. Why do we need to learn about CRO actually for what? Okay, the CRO function actually is to display the pattern of the waveform. Okay, number 2, that can become the voltmeter, because I told you they got Y gain, is it? Y gain is read about the voltage, so that means they can show about the voltage is how many. They also can be the clock, because they got time base. Okay, they got time base. Okay, time base later can show about the time taken. So this one is a 3 function for the CRO. Okay, so from here, and we can see the next one. Next one is a diagram. Okay, I like you to see the diagram is more clear from here. 60. Okay, this one is a diagram. When they say about the time base on or off. Okay, you see, when starting no input. No input means don't have any readings. No input means at the center. You can see the spot cathode ray at the center. Okay, time base off. Off means you cannot read the horizontal. Okay, so you just can see one dot. If I say time base on, that means you can read the horizontal line. Okay, this one we call time base on. Okay, now I put DC, direct current already. Okay, now can you see the spot they go up? Go up means you got reading, but this one is a time base off. When I say time base on, that means now you can read horizontal line. Okay, the horizontal line follow the position of the point. Okay, if I say I'm using AC, AC means alternating current. So alternating current means what? The current later is 2 volt, later negative 2 volt, later 2 volt, negative 2 volt. This one means positive, negative, is it alternating current? So you find it just now the dot, they never stationary at the point. They will up and down, because you keep moving changes of the current direction. So this one we call time base off. You just can see one straight line, because the point of the cathode ray up, down become one straight line. Okay, if I say time base on, now you can see left and right, is it? Now the left and right is the parabolic shape. There's a parabolic shape, they got up and also they got down. So this one is another diagram. Okay, this one is a time base off. Okay, when I see the first one, we know time base off, and also this one is a AC, because they got up and also the down. Okay, another diagram, can you see the sinusoid? This one graph. Okay, this one is a AC also, but time base is on, because you can see left and right. Okay, can you differentiate time base on and time base off is what happened or not? Okay, hopefully you will understand what I'm talking about this one. Okay, then we continue for the calculation. Okay, then we continue with the following. There's a calculation about the voltage and also the time taken by using the CRO. Okay, let's see here. Okay, first one, they say to measure the DC voltage. Okay, to measure the DC voltage, first one, potential difference, you must refer to the Y gain. Okay, this one must be shown by the Y gain. Okay, they show voltage equal to the Y gain multiplied with the H. Okay, let's see here. The Y gain of the CRO that's set by, okay, this one setting 1.0 V, after that dash, then diV. This one, the meaning is 1, okay, example, this one is the boxes lah. 1 boxes, 2 boxes, is it? So 1 division means 1 boxes, represent by 1 volt. So that means when 1 division you up, that one is represented by 1 volt. So this one very important. They show about the ratio or for the every box. If not, you don't know how to know the voltage is how many. So potential difference of the dry cell. Now they're using the dry cell. There's a 1.5 division. 1.5 division actually is how many volt? So you just take this one. 1 division is a 1 volt, is it? So 1.5 means 1.5 volt. So this one is an info bring by the Y gain. Okay, now we continue and see this part. Okay, this one is a screen. They show you the info. Okay, center line, can you see the dot? They go up already. This one situation is a time base off. Remember, time base off, you must see the horizontal line, is it? But this one is a off, so you can see one dot only. Okay, so if I on the time base, you find it there one straight line, also same level, 1.5 division. So this one is how we know 1.5, we depend for the Y gain. Okay, now if I using AC voltage, okay, if I using AC voltage, with more information we can find peak to peak potential difference, or we write VPP, or you can find about the peak potential difference, that's called VP. Okay, so just now we cannot find more, we just can find one of the voltage, the dot up how many, that one is a direct current. Okay, if alternating current, that means you can find two, you can find VPP, you can find VP. Okay, let's see how to find VP and VPP. Yeah? Okay, come. From this one diagram. Okay, this one diagram is a time base off, remember? So you cannot see left and right, you just can see up and down only. So this one we call VP. From the horizontal, if you up until this point, this one we call VP. VP means a peak of the voltage. So if I say one division is a 1 volt, here is a 2 volt. Okay, so VPP means peak to the peak. We got two peak, up one and the bottom one. So that means you just take this one 1, 2, 3, 4. 4 boxes means 4 volt. So this one means by the VPP. Okay, so when I just on the time base, so you can see the sinusoidal graph, left and right you also can see. So this one is a VP lah. From the horizontal you go to the maximum. You also can say this one is an amplitude. Before that you learn. Okay, VPP means from the crest straight forward until the truth. This one we call VPP. Okay, so for the direct current we cannot find about the VP and VPP. We just can find one of the height is how many only. For the AC we still can find about the VPP and also VP. Okay, one more thing you need to know, from the AC we can find the root mean square. Okay, this one we call voltage for the potential difference for the root mean square, the formula. Okay, this one's a formula for the root mean square. Later I go to explain what means of the root mean square. Okay, remember the formula first. Okay, 1 over the square root 2, then VP. Okay, so now we're going to see what means for the root mean square. Okay, I need to write here because no space. Okay, let's see the meaning. Okay, root mean square. Okay, root mean square means AC current, then we can find about root mean square, is it? If direct current, I using 2 volt. Okay, if I root mean square, how we going to do the calculation? Okay, let's see the example calculation first. Okay, if VP is 2 volt, so if VP I say 2 volt, okay, root mean square should be how many? So root mean square we need to do the calculation. 1 over square root 2 multiply 2 volt, is it? So you get the answer is 1.41. So that means root mean square, they can produce the same effect, okay, as a normal, using direct current, using alternating current. Root mean square, they can produce a actual result, but you no need supply more of the volt. So they can, using 2 volt, you produce the same result. If I using the root mean square 1.4 volt, I also can produce the same of the result. So that means I need to count what is the minimum voltage I need to use. Then after that I can produce the same of the result. So that here they're using root mean square to calculation. Okay, so from here the root mean square, they produce same amount of heating energy over the same period of the time for the same resistance use. So you're using the time is the same, resistance also same, but I still can produce the same amount of the heating effect. Okay, although I using less of the potential difference. So this one we can say root mean square, they can save about the voltage. Okay, after that they can produce the same of the effect. So this one how to do the calculation, we just can do the calculation for AC only. DC we don't have any root mean square. Okay, now we go back to see the calculation, how to get it. Okay, so from here the Y gain, info from the CRO, Y gain is 1 volt per division. Okay, if I say peak to peak, what's your answer? Peak to peak, now from the diagram they got 4 boxes, is it? 4 division multiply 1, so the answer should be 4 volt. If peak normally is a half from the VPP lah, so we just divide by 2, then we get 2 volt. Okay, root mean square for the potential difference, they get 1.41. So that means 1.41 and 2 volt, you also get the same result. So this one root mean square, they just want to save about the potential difference. Okay, let's see the example 3. Okay, now the diagram they show about the waveform obtained from the AC power supply. Y input of the CRO. Okay, let's see the info. 20 volt per cm. Okay, we assume one small boxer is 1 cm lah. Okay, we assume this one is a 1 cm. So 1 cm represented by 2 volt. Okay, then the time base also is per cm, 5 millisecond. Okay, so from here we can see the question what they want. Okay, that one is your another page. We can see another page first. Okay, I don't want to show here because I want to show about the diagram. The period of the signal. Okay, first one they want to find the period of the signal. So we start from here, the periods. So important we draw the center line. Okay, if you never draw the center line, you cannot find everything. So now we start from here lah. This one's the bottom. Okay, 1, 2, 3, 4, 4 boxes bottom, 4 boxes up. Okay, this one's the center line. Okay, we start from here. Okay, they want to find period, is it? So we need to count from the left. Okay, this one is the starting point. This one is the ending point. Okay, one complete oscillation. So one complete oscillation, you need to count inside got how many boxes. Okay, I count it. 2, 4, 6. Okay, after that got 8. Then after that got 10. Then 12, 14. Okay, they got 14 boxes for one complete oscillation. So we need to do calculation. So the A periods equal to the 14 boxes multiply 5 millisecond, is it? So I get it as a 70 millisecond. Okay, 70 millisecond. Okay, then we go B. Okay, B they want to find the frequency. So the frequency you convert the millisecond become second. So frequency is 1 over T. So I get it. 70 milli you go to convert. Okay, I get it. The answer is 14.929. Okay, sorry. 14.29 second. Frequency hertz. 29 hertz. Okay, then we continue with the C. C they want to find peak to peak. Peak to peak means top until bottom. Okay, just now we count already. Top is 4 boxes, down is 4 boxes. Suppose it's 8 lah. So I write here C VPP equal to the 8 boxes multiply. Okay, 1 cm represent by 20 volt, is it? So I need to multiply 20 volt. So from here the answer here is 160 volt. Okay, D is peak voltage, so VP. So we just divide by 2 lah. So VP equal 160 divided by 2. Okay, there's the answer 80 volt. Okay, just one of the simple question. Make sure you know, you will see carefully every boxes. Okay, then we continue for the next example question. Okay, let's see the page 5. There's example 4. Okay, the figure they show about the waveform. Okay, waveform they are obtained the screen CRO at the airport radar system. Okay, the point X and Y indicate the time transformation for the aeroplane and the time receiving by the refracted signal. So we can say X also crest, Y also crest. This one actually is a 1 of the lambda lah. Agree, HCM. Okay, time base. They give you the time base, 50 millisecond per cm. Okay, now, first one, the time travel of the radar X to Y. So we will do lah, X to Y, they're using HCM, is it? 8 multiplied with the 50 milli, 10 negative 3, is it? Okay, so finally I get the answer should be, okay, if you never convert, then you get milli lah. If I convert, I get 400 times 10 power of negative 3. Okay, second. Okay, if you never convert the milli, they still do write the milli, but you no need to write times 10 power negative 3. Okay, B. Okay, B, they want to find the distance between the rudder station of the aeroplane, then they give you the speed. Okay, remember the formula, V equal displacement over the time, is it? So I want to know the distance. So from here, the distance traveled by the rudder. Remember, the distance the rudder send should be two-way, because there's a signal. There's send, after that receive back. So velocity for the speed is two-way. Time taken also should be two-way. Okay, the problem is the distance they want to find is one-way. So your formula should be, this one is 2D. Okay, V equal 2D over the T. So you want to find about the D is how many? You must take V multiply the T first, 3 times 10 power of 8, multiply with the 400 times 10 power of negative 3. Okay, then after that, you need to divide by 2. That one is the distance for one way. So my final answer here, okay, distance is 6 times 10 power of 7 meter. Okay, so this one is distance they want to count about for the rudder station. That means this one same like the refraction of the sound wave. Means you send, after that must be received back. So the time taken is a two-way. Then the speed you send also is a two-way. Then the question they just want to find what is the distance. So always divide by 2. Okay, so this one is what we need to learn for 4.1. Okay, I will show you some of the example questions for calculation. Okay, let's see here first. Okay, this one is one of the example question. Okay, let's see this one example question. What is the value for the DC voltage if the Y gain? Okay, they give you info. Okay, the info here is a Y gain is 1 volt per division. Okay, this one info is very important, and if we don't have, we cannot do calculation. So 1 volt per division. Okay, now we're going to see the line. This has a time based on. Can you see one horizontal line? So how many boxes from the horizontal? 4 boxes. So that means your total volt is how many? 4 multiplied with the 1. So total voltage is a 4 volt. Okay, so just a simple question. You need to know how to read the CRO. Okay, then we go to the second question. Okay, the second question, they show you the sinusoid. Okay, you see this one graph. Okay, peak to peak. They want you to count peak and also peak to peak lah. So from here, we need to do the calculation. Okay, first one, we got to find the horizontal line. Okay, the horizontal line is start here. Okay, the horizontal line. Draw lah. Okay, so from here, you need to count lah, how many boxes up? 1, 2, 3, 4. 4 boxes up, is it? So we need to find VP first. Okay, so the VP is 4 boxes multiply with, okay, 3 volt per division. So multiply 3 lah. So this one is a 12 volt. Okay, VPP. VPP total got 8 boxes, is it? 8 multiplied with the 3. So the answer is 24 volt. Okay, just a simple question only. Okay, how to read about the CRO. Okay, then we continue with the next question. Okay, let's see this question. Okay, this one also sinusoid. So what you need to do, again, start with your horizontal line. Okay, horizontal line you draw at the center here. Okay, horizontal. Okay, now, okay, finish. Okay, from this one question, they want to find is so many, got 4 things. So you need to see the info first. 20 volt per division, Y gain. Then this one is a time base. Okay, 5 millisecond per division. First one, we find the peak voltage. Peak voltage, we got 4 boxes, is it? 4 multiplied with the 20. So the answer should be 80 volt. Okay, VPP, 8 boxes, multiply with 20. So should be 160 volt. Okay, now we're going to see the period. Period is a 1 complete oscillation, so we need to count 1, 2, 3, 4, 5, 6, 7, 8. 8 boxes complete 1 oscillation. 8 multiplied with the millisecond, is it? 5 milli. So the answer should be 40 millisecond. Okay, so this one is a time the periods. Okay, frequency you need to convert. You convert becomes second. I don't want using millisecond. So from here, frequency equal 1 over t. So t now is a 40, multiply 10 negative 3. So final answer, I get it, that's a 25 hertz. Okay, so simple question again, and the last one. Okay, the last one, they say the length between the two crests is 3 cm. Okay, simple again. I will draw about the center line. Okay, I draw center. Okay, this one is a crest to another crest is 3 cm. So I can say this one is a lambda lah. Okay, one division is represented by 1 cm. So time base set by 5 millisecond per division. So from here, the Y gain, they never tell you how many volt. They just say 1 cm represented by 1 division. Okay, we find the period first. Okay, period is one complete oscillation. Okay, 5 millisecond. Oh, okay, division. Okay, 1 division means 1 cm. So you got 3 cm means 3 division, is it? We need to count about the periods. We need to 3 division. 3 cm represent 3 division. So 3 multiply with the 5 millisecond. So I get it. There's 15. Okay, millisecond. That one is my periods. Okay, 15 millisecond. Okay, now we need to go to the frequency. When you find about frequency, please no more milli, convert. So 115 times 10 power negative 3. So from here we can check the answer. So the answer here, I get it, there's a 66.67 hertz. The next one is when the frequency of the wave is double. So what is the length between the two crests? Okay, we see the relationship first. V equal F lambda. Okay, if the frequency become double, what you think about the lambda? The lambda become half. Agree or not? Because inversely proportional. So frequency 2 times. Okay, so the period, they ask about the length, is it? So the length should be half. Lambda will become the half. So from here, now the frequency become double. So my lambda is 3 cm, is it? So you find it, the lambda now will become 3 over 2. There's a 1.5 cm. Okay, so this one is the answer lah when you want to find about the wavelength and frequency, what's the relationship. Okay, so our lesson just until here only. So what you need to do should be the tutorial. So the next lesson I will show you about the tutorial answer. Okay, so we go back to our screen. Okay, so everyone, say hopefully you understand what I'm talking about. So continue with your tutorial 4.1. The next lesson I will show the show about the answer about this one 4.1 answer and objective and structure lah. So thank you for your watching. So bye.